Hey guys, hi. So in the last few videos, we have been seeing iterative based sorting algorithms, mainly which were falling under the comparison based sorting algorithms criteria. And we saw bubble sort, selection sort, insertion sort, and then we saw custom comparator as well as lambda functions, right? We also saw multiple patterns which we can use in order to solve complicated sorting problems, right? Now in this section, we will be looking at non-comparison based sorting algorithms. Okay, so what actually is non-comparison based sorting algorithms is, in comparison based sorting algorithm, we compare two different numbers. Let's suppose we have given a list of numbers x1, x2, x3 until xn, right? So in comparison based sorting algorithms, we generally compare these two numbers, do a comparison, and then deduce the result. Now this is what we were doing in comparison based sorting algorithms, right? Now comes non-comparison based sorting algorithm, wherein instead of comparing any two numbers, we come up with some different criterias, right? What are these criteria? We will see in the upcoming videos. But here, instead of actually comparing two different numbers, we come up with a different criteria and then sort the numbers, right? So in general, in non-comparison based sorting algorithms, we have three different algorithms which we plan to discuss. The first one is bucket sort. Then we have counting sort. And then we have the third one, which is radix sort. So we will discuss these three sorting algorithms and see how, without comparing two elements, we can deduce the either a certain order into the given list of numbers, right? So we'll start our discussion today with the first one, which is counting sort, right? So what actually is counting sort? Counting sort, as I told you, in non-comparison based sorting algorithms, the criteria is that they generally works on a specific data set and they work in linear time, right? So the USP here is they only work in specific data set. Now what is this constraint? We'll see, like this will also depend upon a particular algorithm which we're discussing, and they generally have a linear time complexity. But since they only work on a specific data set, we cannot generalize these algorithms and use it for a wider set of data, right? So the first thing is, the first algorithm which we plan to discuss is counting sort. So what happens in counting sort is, let us suppose I was given some numbers. Now how we can sort these numbers, right? If you see, there is a certain pattern which are getting followed, right? So what we do in counting sort, we basically count the number of occurrences of each of these numbers, right? So we see, okay, 7 is occurring how many times? 1, 2, 3, 4, 5. We saw, okay, how many times 8 is occurring? 3. And how many times 9 is occurring? 1, 2, 1 and 2 only. So then if we have these numbers, we can just write them, right? And this is the basic idea behind counting sort. Okay, so this is just a small example, although like there will be some complicated example which you will see here, but this is just one small example of how we can implement counting sort. Counting sort, if we talk about counting sort in a more generalized fashion, counting sort generally works upon the range of numbers. So counting sort is applicable if the range of numbers is given. Okay, so what we do in counting sort, we actually create an auxiliary array of size k. Now what is this k? This k is actually the range of numbers. What is the range of numbers? The range of numbers should be max minus min plus 1. What is max and min here? Max and min here obviously will be, max will be the highest number, min is the lowest number in the given set of numbers, and yeah. Okay, so we create an auxiliary space of size k, and then we go through the array again, whatever array is given to me. If array is given to me like a1, a2, a3 and so on, I will go through this array one by one and increment the corresponding value in the auxiliary array. right? Once I increment the auxiliary array's values, I can just go through the auxiliary array again and take out the value and push it into the original array. Now let us see through an example. So if we see this example only, wherein I have these set of numbers, I will create auxiliary array of 3 numbers. Why 3 numbers? Because if we see what is the max here, 9. What is min here? 7 plus 1. So this will give me 3. Right, so I have to create an auxiliary array of size 3. Now I go through 7. Okay, 7 is there. Increment 7 by 1. 7 is there. Initially they all will be 0. And we keep on incrementing them. So increment 7 5 times and it will become 5. Increment 8 3 times and it will become 3. Increment 9 2 times and it will become 2. So once I increment all of these numbers, I will just iterate through the auxiliary array, whatever I have created in my counting sort, and push them into the original vector. So we can replace these value only. We can replace this value into the original array. Okay, so if we look here, how much space are we consuming? We are consuming this much space only, right? This much space I am consuming. And what is the size of this space? This space would be O of k size, right? So if you look at the time complexity of this particular algorithm, what is the time complexity going to be? There are 3 operations which we need to do. Okay, I'll just write down each of the operations. The first operation is create a auxiliary array and initialize with 0. Okay, auxiliary array of size k. The second operation would be go through the original array and increment corresponding value in auxiliary array. This is my original array basically. Increment corresponding value in auxiliary array. What is the third operation going to be? The third operation is generally just put back the values from auxiliary array to original array, right? Auxiliary array to original array. How we can put back the values? We can just iterate through it, right? How we can iterate? Okay, 7 is coming 5 number of time. We'll just increment 1 7 7 7 7 7. 5 times we'll push 7. Then 8 is coming 3 times. I will push next 8 3 times. And then 9 will be pushed 2 times. So this is how we will push back the values, right? So if we see each of this operation, how much time we are taking in this operation, this will be O of k. Since we are creating an auxiliary array of size k with initializing all of them with 0. How much time this will be taking? Think about it. This will be taking O of n time. Why? Because I am going through the original array one by one. And how much time this will take? This will again take O of k plus n times. Why it is taking k plus n time? Because it might be possible that I have to put back the value, like what all the values will be pushed back into one bucket only, right? So worst case scenario, it will be O of k. So if we look at the overall time complexity for counting sort, it will come out to be O of k plus n. And since k is always less than equal to n, we can consider it to be O of n, right? What is the space complexity here? Space complexity would be O of k, right? Since we are taking an auxiliary array of size k, in worst case scenario this could be n as well, right? Is it stable or not? Yes, it will be stable in nature. Why it is stable in nature? We can easily make it stable by making sure that we are actually pulling back the value which was inserted first. So this algorithm is stable in nature. Yes. It is in place? No, this is not in place. So that's about this algorithm, counting sort. I have a question for you before we leave this video. The question is, how can we apply counting sort for negative numbers? Just think about it. Anyway, if you get the answer, you can start with the next video. So in the next video, we'll start with other non-comparison based sorting algorithms. Thank you.